My name is Dr. James Wotton and I am a theoretical physicist at the University of Basel. Being a theoretical physicist means that I mostly think about things and sometimes write them down. But this week I did an experiment, and you can do it too using the IBM Quantum Experience. So I'm going to tell you all about my quantum experience so you can maybe have quantum experiences of your own. My experience starts with this paper which I published not too long ago in the Journal of Physics A. It's called A Family of Stabilizer Codes for DZ2 Anions and Majorana Modes, which you probably don't understand, but you don't need to. The main thing is that near the end of this paper I proposed an experiment that I wanted to convince people to do at some point. This week I realized that using the IBM Quantum Experience I could do it myself. The IBM Quantum Experience is based on a processor of 5 qubits, so before we begin we probably better look at what a qubit is. A qubit is just a quantum version of a bit, and a bit, as you probably know, is something which is either 0 or 1. We don't have to call it 0 or 1, we could call it any two labels we like. High and low, up and down, cheese and flamingo, it doesn't matter. The only thing is it has to have two states available to it, and then as long as we use it for some information theoretic thing, like computing or communicating, then it is a bit. So a qubit is a quantum version of a bit, which means that it can not only be 0 or 1, but some superposition of the two. So a bit or a qubit only has these two states, 0 and 1, available to it. It can't be anything else, but it's just that a quantum bit can be both at the same time in some sort of weird quantum way. So the best way to think of a qubit and these weird quantum things is using a ball. So the state 0 could be this weird 1 thing pointing up, and the state 1 can be this weird 1 thing pointing down. So here we start off with the state 0 and then we measure it in the Z basis. A measurement in the Z basis just means we ask it, are you up or down? If we have an X here, an X is the rotation that rotates up to down and down to up. So let's have a look at this ball now, and we find that it's pointing down because we rotated it to down. So this pointing down is the state 1, although we can just stick with the labels up and down because they'll actually be easiest for us in this case. If we look at a Hadamard is a rotation that rotates up to left. Now if we look at that, we see that the weird 1 thing is not pointing in the left direction in this depiction, because one other way that you can think of the weird 1 thing pointing left is as a superposition of up and down. So what this means is, if we were to measure it in the up-down basis, if we were to ask it whether it was up or down and it was left, then it can't just say, well, I'm neither actually, mate. It has to decide whether it's up or down. And because it's equally between the two, it decides either one with a 50-50 probability, as we can see here. If it were pointing in a direction that was closer to up, it would be more likely to go for up. If it was pointing in a direction that was closer to down, it would be more likely to go down. We can also think of the states which are not just left and right, but also forwards and backwards. So we would get that by doing a rotation that achieves those, which is this rotation, first an S and then a Hadamard. But you don't have to worry about the technicalities of that. Basically, we have this sphere, and we think of pointing up as one state available to us, and pointing down as another state, and we can ask it, are you up or down? Also, we can think of pointing left and pointing right as two available states, and we can ask it, are you left or right? And we can think of forwards and backwards as two available states, and we can ask it, are you forwards or backwards? Because these directions oppose each other, we are allowed to ask whether it is one or the other. We can't ask, are you up or pointing in that direction though, because they aren't opposites. So these are 3 types of measurements we can make. We can actually make a lot more than this, but these are the 3 types that we'll be concerned about in this video. This is called a Z measurement when we measure along the Z axis and ask if it's up or down. It's called an X measurement when we measure along the X axis and it's called a Y measurement when we measure along the Y axis. Now, one thing about X, Y, and Z measurements is that they do not commute. So commute means that it depends on which order we do them in. We can't do a Z and then an X and expect it to give us the same results as if we did an X and then a Z. And the reason why is that, say we have something pointing up and we measure it in the Z basis, then it will of course say it's pointing up. But then if we were to measure in the X basis, because pointing up is equally between left and right, it would have to randomly choose to be either left or right. So we start off pointing up, we do a Z measurement and we definitely get the result up, and then we do an X measurement and we get a random result. But if we first did the X measurement, then we would get the random result just as before, but because it is not, say it chooses left, then if we do a Z measurement, it's equally between up and down, so that is also a random result. So that's a different result that we would get than if we did it the other way round. So this non-commutation is an important thing in quantum mechanics. It's the basis of measurements changing things, which is something that you often hear about quantum, and it's something that we're going to use in our experiment today. 2 qubits, we can do even more fun things. Here we have a controlled knot, and I should also say, why is there 2 lines coming out of these measurements? Well, in these quantum circuits, this is a quantum circuit where we put the input here and then have lines depicting the history of the qubits as they go through all of these operations. When we have 2 lines, that depicts a bit, a piece of classical information. 1 line depicts a qubit. So an actual quantum qubit is going in here, it gets measured, but afterwards you only get 0 or 1 out. So in the previous little bit I referred to states up and down because that made a little bit more sense on the sphere when I was discussing superpositions, but from now on I'll go back to the standard using 0 and 1 instead of up and down, except for where I don't, so be on guard, I'm only human. What we have here is a controlled knot. What a controlled knot does is it looks at this qubit, which is the control, and it does something to that qubit, which is the target. It does nothing to this qubit, it just has to cross that because it's interacting these two, but it's not actually talking to this one. So what it does specifically is it looks whether this is a 0 or a 1, and if it's a 0, it does nothing here. If it's a 1, it does an X. So in this case, this is a 0, and this is a 0. This is doing nothing, so they should both come out 0 when we measure the Z basis and see if they're 0 or 1. And if we look at the results, what we find is, indeed, the only thing that ever happens is they both come out 0 with probability 1, exactly as we predicted. Now if we were to rotate this guy to be 1 instead of 0, then this would see a 1 and do an X here, which rotates that that 0 to a 1. So if we look at this, we find that indeed the only thing that ever happens is 1, 1, because now we've rotated the first one to be 1, and the controlled knot similarly rotates the second one. It's kind of copied it onto here. Now what happens if we have C knots on 2 qubits? So both these ones here. What this can allow us to do is a 2 qubit gate. We'll find that whenever these two are the same state in the Z basis, this will output 0, and whenever they're different, this will output 1. So we can see that if they're both 0, then both of these do nothing, so this will obviously remain the 0 it started. If these are both 1, then they both cause an X to be done here, and X rotates 0 to 1 and 1 to 0, so by doing 2 you rotate from 0 to 1 and then back from 1 to 0, so the net effect is also nothing. So 0, 0 gives us 0, 0, 0. So 0, 0 on the first two gives us 0 on the second, on the final one here. But also, if they were both 1, we would also get 0 on the final one here, because all that the final one cares about is that they are the same. So here, in every... what the hell did I do? I put a couple of Hadamards there instead of X's. So what these Hadamards did was they created a superposition of 0, 0, 0, 1, 1, 0, and 1, 1, because the Hadamard rotates 0 to a left state. A left is a superposition of 0 and 1, so it rotated us to this big superposition of 0, 0, 0, 1, 1, 0 and 1, 1, which is a bit of a more advanced lesson that I didn't want to get onto quite yet, but let's skip ahead and do it now instead. So what this does is it sees that when these first two are 0, 0, then the last one is 0. When the first two are 0, 1, the last one is 1. When the first two are 1, 0, the last one is 1. And when the first two are 1, 1, the last one is 0. So always when they're the same, it gives 0. When they're different, it gives 1. But an interesting thing about this is that it preserves superpositions. So it starts off, well, if we threw these measurements away at least, what it would do is preserve superpositions. Initially we have a superposition of 0, 0, 0, 1, 1, 0 and 1, 1. We do this measurement which tells us whether these are the same or different, and if it tells us same, this is consistent with both 0, 0 and 1, 1, so what comes out here is that superposition of 0, 0 and 1, 1. So they're still superpositioned, that's not a word, but they are actually now entangled. They share this correlation in their superposition. So this is a way that we can do a measurement in which we just extract the information about whether they're the same or different without otherwise disturbing the state. We call this a ZZ measurement. Another thing we can do is what's called an XX measurement. So this looks again at whether they're the same or different, but this time using the X basis. It looks at whether their lefts and rights are the same. What we do if we want to do one of those is put a couple of Hadamards either side of the control end. So I can just put that Hadamard there because the fact that this crosses it doesn't actually matter. Now we've put these Hadamards either end of the control, and what this means that instead of this looking at Z, it's rotated so that it looks at X, and then we rotate back at the end. So this is an XX measurement. It will look at whether they're left and right, and if they're the same, if they're left, left and right, right, it'll output 0 here, and if they're different, left, right and right, left, it'll output 1. And we can also do the same thing with the Z basis. We just have to stick some S's in here as well. Sorry, did I say the Z basis? I meant the Y basis. So we can do ZZ, XX and YY measurements, and they are exactly the kind of measurements that we are going to do in our experiment. Let's move on from 2 qubits to a whole boatload, and these are going to be arranged on a honeycomb lattice, or a hexagonal lattice as some call it. So it's going to be a big old hexagonal lattice which stretches as far as the eye can see, but let's zoom in on one particular bit of it. This image is from a paper that I have written, so an explanation I've written of my experiment, and you can find it in the link below. I've tried to write it so that it's good for both professionals and amateur scientists. So here we have a few bits of sections of the honeycomb lattice. This reminds me of Majora's Mask, so I call it Majorana's Mask. That's a joke that you are hopefully going to appreciate later. Anyway, each dot here is a qubit. It represents a qubit. So the black ones are on the vertices, which are the places where the lines meet. They are called vertex qubits. The red ones are on the lines, so they are, or edges as we call them, so they are called edge qubits. And the grey ones sit in the middle of these hexagons, so we call them hexagon qubits. So the black ones are our code qubits. They're going to be part of a quantum error correcting code, which we're not going to go into too much detail about what one of those is. The red ones help us make 2 qubit XX, YY and ZZ measurements on these code qubits. So this red one will do an XX measurement of these two, this green one will help us do a YY measurement of these two, and the blue ones help us do ZZ measurements. In general, we would also want to do a measurement of all 6 code qubits around the plaquette. So we would do a controlled knot type thing between these two, and then 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 measure that one. But we're not going to worry too much about these this time, because that requires 7 qubits, so it's beyond what the IBM Quantum Experience can give us. Now, one thing to note is that these measurements don't commute. This XX measurement and this ZZ measurement, which meet on only 1 qubit, do not commute with each other. We can't make a state which we know will definitely give us a result 0 for this one, and then measure this one, and then expect it still to be in a state where if we measure this one we will get a 0, because by measuring that one that doesn't commute, we would have messed up this one and the outcome would now be random. But what we want to do is prepare a state of these many qubits which is going to have definite results for some of these edge measurements. So what we have to do is pick a subset of these edges which we're going to use to make the measurements, and we just ignore the other ones. And we need to choose them so that all of the qubits are involved in at least one of these measurements. So the easiest way is just to choose all of these Z ones on the vertical links. Here's a new picture to represent that in a bit more of a simplified manner. We've got rid of the qubits here, and we've just got these blue oblongs. No, not oblongs. They're what are they called? The long circle things? Whatever they are. We've got them to represent the ZZ measurements, and of course, in general, we'll also be making these big horrible plaquette measurements. So let's say we prepare a state in which if we measured these, they would all come out 0, and if we measured the plaquette measurements, they would also all come out 0. They commute with the Z measurements. You'll just have to trust me on that. Now, if we were to take a Z rotation and do it... Why isn't it moving? Come on, here, Zeddy, Zeddy, Zeddy. If we were to take a Z rotation and do it right there, what would happen? Well, firstly, what is a Z rotation? We've had X rotations before. They're the ones that rotate up to down and down to up. A Z rotation is a thing that rotates left to right and right to left. If we do a Z rotation here, what we would find is that if we measured that guy, it would still give 0 because Z commutes with a ZZ measurement. If we were to measure here and here though, that 0 would have become a 1. So let's put one of these in the middle to denote that these are now 1. That should have copied, but it didn't. I'm on a Mac, and on a Mac you have to do Control-C and Control-V on this program instead of Command-C and Command-V, and it just confuses me because it's what it should be instead of what it shouldn't be. And everything should always be what it shouldn't be with Apple products, right? Anyway, we do a Z there, and it creates these two places where the measurement is not what it should be. It's a 1 instead of a 0. If we were to do another Z here, see, I had that problem again. I did Command V, but it just sort of V and interpreted it as I want to rotate vertically. If we do another one here, what we would find is that this would go back to 0, but this would be giving us a result 1 instead. So we have effectively moved that weird measurement thing here. And if we were to undo this Z, so if we were to do another one another one on top to get rid of it, then this would effectively move from there to there. So these are behaving a little bit like particles somehow. We can do a Z which creates a pair of them out of the vacuum, and then we can move them around. And they're each other's antiparticles, is one thing we can tell because they were created out of the vacuum together. And if we undid this Z, they would both annihilate to the vacuum together. And they're the same type of particle. We know that because we just moved this one here. So both this one and that one have both been here. And because they're in the same position, and because our measurement of them, which is just getting a 1 instead of a 0, gives us exactly the same information, they're completely indistinguishable. So they're the same kind of particle, and we can move them around. Of course, they aren't really particles in the same way that electrons and snooker balls are. They're what we call quasi-particles, because we're just measuring some collective property of the qubits around here, and we're getting some result, and we're just finding that that result somehow acts like a particle. We can think of it like a particle, we can do things to it that we can do to particles, so it's what we call a quasi-particle. So we get particles that live on here, but there's no way to move one of these from here to there. Any rotation we do, we can't do that. But if we started out by looking at particles on these guys, so let's just pretend we started over here, and let's make it a different color. Then what would have happened is that Control C, Control V. If we do a couple of correctly chosen rotations here, we can move this guy to there. So we can't move it to the line above, but we can move it to 2 lines above. And similarly, these ones here, we could move those to 2 lines above. So the particles that live on this row are not the same as the particles that live on this row, because we can never move one to the other, but they are the same as the particles that live on this row. So we have 2 types of particle living on plaquettes. Each of them are their own antiparticle, because they come out of the vacuum together, and they can be annihilated back to the vacuum together, but depending on which row they live on, they're either one type of particle or another. Now these are the so-called E and M anions of the surface codes, and they're the ones that we're going to build quantum computers out of one day. You mark my words. But because we're ignoring the plaquettes, we're not really going to be thinking about those E and M anions. We're instead going to be thinking about what lives on these guys. If we measure these as a 1 instead of a 0, then these have a type of particle on which is a fermion. Now, E and M anions are something that are actually impossible in our universe, so they seem like they're a bit more interesting. These are just fermions, which are a bit boring. We have fermions in the real world, like electrons and things. So why are those the ones that we're going to focus on? Well, now it's time for me to tell you about something called the Ising model. Now it's time to get serious. Now it's time to move over to the blackboard. Hello, by the way. Now, let's imagine a universe in which a type of particle called a Majorana exists. We're going to denote that by a sigma. And the thing about these Majoranas is that they are their own antiparticle, so that we can get a pair of them emerge from nothing. We could have had the vacuum, and then poof, 2 Majoranas emerge in the universe. Now, if we were to recombine them, we would also get nothing, because they started out as nothing, we didn't add anything to it, so now they return to nothing. Now let's say we had another type of particle that can exist in this universe, and that is a psi. We're going to call it a psi. This is a type of fermion. Actually, let's move psi over a bit. We've got plenty of space. Why am I doing it so cramped? Now what we could do with these psis is we could make them decay into 2 Majoranas. So we can have a Majorana that's just been created from nothing. It's 2 Majoranas which emerged out of the vacuum, but we can also have 2 Majoranas which came out of a fermion. And there's no difference between these Majoranas and these Majoranas. If we went over and checked everything about them, they would look exactly the same. The only way you can tell the difference is when you combine these, they become the vacuum, but this just rebuilds that fermion psi. So this could be good for computation or communication, because one thing we need to do is store a bit or a qubit in a way that is good against noise. So it protects the qubit from noise. If we have some little gremlin that comes along here and tries to mess about with our stored bit, it can't. It can only do something if it looks at them both, because there's no way locally, there's no way just by looking at these particles to see if they would fuse to the vacuum or a psi. So if we use this to store our 0 and this to store our 1, and we kept these particles far apart, then there's no way that noise could figure out which is which. There's no way that noise can actually affect it. So storing information with these particles would be pretty awesome because of this weird property they have. Now, another thing is that if we were to take one of these and move it in a loop around one of those, then if we were to combine them after this, if we combine these, they would come out with a psi, and if we combine these, they would come out with nothing. So actually, these particles have never touched. We just made this one dance around that one, and the effect of that dance was to kind of move this psi from here to there. So what we did effectively was a bit flip over here and a bit flip over there. So not only do they store information, but by dancing them around each other, they can process information. And actually they can do quite important operations that we need for quantum computing. So these make good qubits protected against noise, and by dancing them around each other, we can do interesting things for a quantum computer. If these particles were to exist, they would be awesome. The trouble is, they kinda don't exist, and they're kind of actually impossible. And the reason is, here we have a loop around a point, and in 3 dimensions, if we have a loop around the point, we can just pick up the loop, move it over the point, put it down where there's no point, and this means that in terms of topology, a loop around a point is equivalent to a loop around nothing, and so it can't have any interesting topological effects. This means that particles can't do this sort of thing in our 3-dimensional universe. But if we could build a 2-dimensional universe, then maybe they could exist. So we'll come back to how we build a 2-dimensional universe later. There's just something more I want to tell you about these particles. So let's say we have a couple that emerged from the vacuum, and another couple. Well, that Sigma's a bit dodgy, but I'm recording while holding a microphone and doing things on the board, so I hope you can forgive my dodgy Sigma. If we combine these two, they would go back to vacuum. If we combine these two, they would go back to vacuum. But what if we combine these two? They've never seen each other before. They have no history together, which tells them they should go back to vacuum. And so these would actually either go back to vacuum, or they would become a psi. They would do one or the other. They would randomly choose, because they have nothing to actually, no history to tell them which to do. And actually it turns out that this measurement doesn't commute with these measurements in this quantum way. These behave like a qubit. Measuring these would be measuring the z basis of the qubit, but measuring these, that would be an x measurement of the qubit. So that's quite interesting. But another interesting thing is, if you was to then combine these two, it would always give you exactly the same result as you got here. So let's say we combine these two, we got nothing. If we combine these two, we will also get nothing. If we combine these two to get a psi, we would also combine these two to get a psi. And the reason is, we started out with nothing at the beginning, so we have to end up with nothing at the end. So that if this comes out with a psi, this has to come out with another psi, because these psis are also their own antiparticles, so we can combine these to be nothing again. So this correlation is exactly what we're going to be looking at in the experiment when we combine these Majoranas together, because we are going to make these Majoranas. They don't exist in our universe, but we are going to make them. I just realised that you can't see that top bit of the diagram, so there it is. It's not that interesting, you didn't miss much, to be honest. Majoranas are a kind of particle called anions. Anions are the kind of particles that have these cool properties when they dance around each other, and so are not possible in our boring 3-dimensional universe. They are specifically from an anion model called the Ising model, or Ising model, if you want to pronounce it correctly. There are other anion models. One is called DZ2. DZ2 is a great anion model. It has these anions called E and M, and hang on, where have I heard of those before? Didn't we got them when we looked at our Honeycomb lattice model. So the answer to how can we build a 2-dimensional universe in which anions can live is something that we've already seen actually before. To build a 2-dimensional universe, what we can do is just build a 2-dimensional thing in which there are quasiparticles, and those quasiparticles, because they live in their own little 2-dimensional universe, they can behave as anions. So we have this DZ2 model, which has these E and M anions living on these rows, and these fermions living on these links, these edges here. Now those fermions are exactly the same fermions as the ones in the Ising model. So we can ask the question, can we break those fermions so that they decay into 2 Majoranas? I think the reason I've come back to Fig 1 is to make some sort of Majoranas mask pun again. But let's just go beyond that, come on. We need Fig 3. Stop being so obsessed with puns, James. So, how are we going to break these things? Well, if we're right and we can associate each of these things which can contain a fermion or not with Majoranas, then we can think of there being two Majoranas living on each of these edges. Living not really like the qubits are, but effectively like quasi-particles. And if we have two Majoranas living on here and we have two Majoranas living on there, then when we make a state so that these always tell us the result 0, that's like two Majoranas that combine to vacuum. When they tell us 1, that's two Majoranas that combine to a fermion, and the same over here. But if we want to somehow free a couple of these so that they can walk around, what we could do is combine these two Majoranas. So then they would get bound up together, and these ones would no longer have to obey the rule that these two are forced into either definitely fusing to vacuum or definitely, I say fusing sometimes as a synonym for combining. So when we know that they definitely combine to vacuum or definitely combine to a fermion, then these two are very much bound together. They have to agree on what they're going to do when they combine. If we're going to move these things around, we're going to have to sort of freedom from that a little bit, freedom from always having to agree with the one on the same link as them. So we can do that by forcing these two to agree instead. So these two have never seen each other. If we make a measurement which fuses these two, then they will give us some random outcome. If they give us a fermion, well, that's just a fermion that we have to tidy up later. If they don't, then, well, that's good. And now this one will have become free from its bondage of having to agree with that one. This one will have become free from its bondage of having to agree with that one. And by doing more such measurements, we can move them around and let them be truly free. So we need to find some sort of measurement which corresponds to combining these two. So what it has to do is anti-commute with this measurement, so not commute with this measurement, which corresponds to combining these two, and not commute with this measurement, which corresponds to combining these two. And we know indeed such a measurement. It's the XX measurement of this line. So instead of making these measurements, we're going to stop doing those measurements, and instead we're going to make a measurement here. And by changing that, by changing the kind of measurements we make on the links, we end up with these two places where there is no edge measurement. Sometimes I say link and sometimes I say edge. Sorry for throwing around synonyms so much. But we have something where there's no link and no edge measurement, and that corresponds to a Majorana that's free to go about its own business. So we can think of this as two Majoranas. If we combine these two Majoranas, then this one that effectively gets teleported over here. So what we actually do in this case is we look at these two Majoranas and we combine those two, and then this one effectively gets teleported up here. So it's exactly the same as I've just been saying, but on the other side. So why do we think that this one is teleported there? Well, the identity of this one kind of corresponds to what it does when it combines with that one. And if this comes out as vacuum, then we know that, these four things are isolated with the rest of the universe. So if these combine to nothing, and these also in the beginning combine to nothing, then these two must combine to whatever these two initially combined to. So it means that effectively this Majorana has been moved there. Okay, so ends probably the most technical part of all of this. If you didn't understand that, well, let's say if you did understand that, I am amazed. But let this be just one more resource for you to consult in trying to understand that. Other things being the paper that I showed you before, which unfortunately has lots of maths in, and of course this paper, which you can also consult. And I'll probably try and do a blog post on this too, because this is the kind of thing that needs a bit of technicality. Anyway, this is basically it. If you want to move that guy, we can think of these as two Majoranas. If you want to move that guy there, then you just do this measurement. and it moves. We can move these things around, we can braid them, we can dance them around each other, we can keep them well separated to keep our qubits error free. We could do all kinds of things. Or there, actually, I said qubits. So of course qubits live on the vertices, but those are quite noisy qubits, so we have to take many of those qubits and use them to build new qubits that have less noise. So we're going to have the qubits that we are storing inside the Majoranas that we build out of qubits. That's one of the things we have to worry about when we're building quantum computers. Anyway, this is an exchange operation going on here. This is something we can do. We have these two, which initially would combine to vacuum. These two, which would initially combine to vacuum. By doing this measurement, we move that one up there. If we subsequently do this measurement, it would move this one over here. And then if we do that measurement again, everything is, all the Majoranas are back to where Majoranas used to be, except that these two have swapped. We've exchanged them. So here, if we measured these, if we combine these, they would give vacuum. So with these ones, but now these two have never seen each other before. They give a random result, either vacuum or a fermion, and these will always give the same result because ashes to ashes, dust to dust, being a very important physical law in this case. So we will get a correlation between these two. So if we can do this exchange and we can measure this correlation, it will show that we have done some braiding of Majoranas, which would be pretty awesome. But you'll notice that pretty much everything is only going on these 3 qubits, 1, 2 and 3, and their friend qubits on the edges, which are helping doing the XX and YY measurements here. So there's only 5 qubits that are really involved. Well, this one's also involved in order to do the ZZ measurement here, and these two are also involved in order to do these ones. But if we just truncate the whole thing to these 5 qubits, we can actually shorten these ZZ things to, instead of ZZ on 2, we can just shorten it to a Z on 1, and here we shorten it to a Z on 1, and here we shorten it to a Z on 1. So this whole process of taking 2 Majoranas, swapping them, and then looking at the correlations that result can be done on just these 5 qubits that exist there. And that is pretty awesome, because 5 qubits is exactly what we have in the IBM Quantum Experience. And the state where we initially have, we combine these and they give vacuum, now corresponds to just a 0 on there, a 0 on there, and a 0 on there. So we just have to start with these black qubits being 0, these edge qubits being 0, and then doing an XX measurement, and then doing a YY measurement, and then doing a Z measurement, and then doing Z measurements here, and finding correlations. And that could be done by this circuit here. So this is a controlled knot which looks in the X basis, and so these two together are doing, in the Y basis, these two together are doing a YY measurement, and that is the actual measuring out of it. So this is doing it on V1 and V2, which are these 2 qubits here, 1 and 2, the vertex qubits 1 and 2. And then we do an XX measurement on 2 and 3, so this is the XX going on here, using the Hadamard to rotate it into the X basis on 2 and 3. And then we need to do this Z measurement here, so we do that. That's just a Z measurement on qubit 2, which is this one here. And then we do Z measurements on 1 and 3 in order to look at these correlations. So these are looking at combining the two Majoranas, seeing what random result they get out, and confirming that they are correlated. So this is basically just the circuit we need to do. We have to take 5 qubits, do this circuit, and we have braided 2 Majoranas. We have created 2 impossible particles in our own 2-dimensional universe. We have exchanged them, and then we have found the correlations that should exist. So that's pretty cool. We have 5 qubits in the IBM Quantum Experience. Let's do the experiment. Alas, nothing in life is quite so simple, and to be honest, braiding two impossible particles on our own quantum two-dimensional universe is probably not something that you expected to be simple anyway. Even though we have 5 qubits, the qubits that we can use in IBM's 5Q quantum processor that we can control through the IBM experience has certain limitations. One is that we can only ever do a controlled knot so that the control is not the middle qubit and the target is the middle qubit. And also, each of the qubits has its own strengths and weaknesses. Some of them have longer lifetimes than others, because all of these qubits are subject to actual realistic noise, and some of them have more noise than others. So this one, for example, is quite short-lived, whereas these ones are quite long-lived. So we're going to have to think about which ones we use for which purposes, depending on how long they're going to be needed for. So what we do is we use this this E12, as I've called it, as E1. So it's going to be used as an intermediary for this YY measurement. We're going to use the top one as V1 and the bottom one as V2. So we do here the YY measurement, except that we don't actually measure at the end of it, because if we measure it here, we can no longer use this qubit and we can no longer do any controlled knots. So we don't want to do that. So what we do is a controlled knot which copies that result over to this E1 here. Now you would do a copy using a controlled knot with a control here and the target there, but we can't do those. So to make the controlled knot go backwards, we can just do Hadamard's either side of both the control and the target. You'll have to trust me on that. You'll need the maths to see that. So we copy it over here and we measure there, and then we do the XX operation, the XX measurement on V2 and V3, and then we measure there, although that measurement will be both the measurement value of the XX measurement and the YY measurement, but because we also know the YY measurement from here, we can infer what the XX is as well. And then we measure V2 as we need to here, and then we measure V1 and V3, but there's no point in having this one just sit around for ages before we measure it. So we do the measurement as soon as we possibly can to get the best result possible, and we do the measurement here as soon as we possibly can. So this is the implementation that we're actually going to use. It has the same effect as this, but it's more squashed up, so everything happens as quick as possible, and we have this rubbish qubit with the stuff that doesn't take so long, and we have these better qubits with the stuff that takes a bit longer. So this is what we're going to do, and basically we just put this into the IBM Quantum Experience, we press run, and off it goes. Here is the circuit in the flesh on the IBM Quantum Experience. This is the thing that's going to tell their processor how to create and manipulate these particles that are impossible in our universe. So let's just go to run and run it for 8,192 shots. Off it goes. I've already got some results from before, so let's do a new execution, and there it is. It's the next one to run. So pretty much right now, as I'm talking, those Majoranas are getting braided, which is pretty awesome. Now if you think that's not awesome because it's not happening while you're watching, because this is a recording, then do it yourself. Do it yourself and you will be braiding Majoranas. Now let's see what the results should be. Let's simulate it, ideally, which means without any noise. And what we find is that if we ignore the middle qubits, so the middle qubits are the ones that see any stray anions that get created along the way. Sorry, not anions, but fermions. Any fermionic mess that gets created along the way, these ones will see it. So let's just concentrate on the examples where there's no fermionic mess in the middle. In that case, this one, which is V1, and this one, which is V3, when we measure these in the Z basis, that combines these two pairs of Majoranas, and they should randomly either give us a vacuum or a fermion, but they should always give us the same thing. So here's the example where the fermionic mess is all 0, so there's no fermionic mess, and both of the pairs are becoming vacuum, and this has a non-zero probability. And in this case, there's no fermionic mess. One becomes vacuum, one becomes a fermion. That has no probability, because that's one of the examples which is impossible, because they always have to come up with the same thing. Here's two more examples with no fermionic mess. Here they both come out fermion, non-zero. Here one comes out fermion, one vacuum. That has a 0 probability. And you see that the probabilities that they both come out vacuum and they both come out fermion are the same. They're both this 0.63. Let's now do the simulation where we simulate it under realistic conditions. So this knows a little about what the kind of noise happens in the experiment and does it in the case that there's noise. Here we see that there is some probability that one comes out vacuum, one comes out a fermion. So that could be some fermion got created by some noise process, or that our measurement there lied. But the probability that they both come out vacuum is a lot higher. And over here, the probability that they both come out fermion is a lot higher than one coming out vacuum, one coming out fermion. We see that there's a little bit of a bias towards them coming out vacuum rather than both coming out fermions. This is because these qubits tend to like to become 0 as fast as they can, or because these qubits like to be in 0, they're going to try and decay back down to 0. So one of the bad things that's happening is that they are, with some probability, decaying back down to 0. So they are slightly preferring this one than this one. Now, let's see if we have our actual experimental data. Yep, so this is the one that ran at 11:24. This is one that ran in the previous take, so let's ignore that one. And let's see what the data tells us. Well, here we have, so this is actual. No, it's not. This is a simulation. What am I talking about? This is the experiment. There is some experimental data from a previous take, but as I say, we're ignoring that. This is the experiment that we just ran just now live, and we see that both fermion is coming out higher than one vacuum, one fermion. But these two are pretty much the same. So both vacuum is coming out higher than one of them being a fermion. Both fermion and one fermion are pretty much the same. So we're definitely seeing a correlation, but it's not a very strong correlation, because the noise in the processor today, it seems to be quite high. That kind of noise which makes them decay back down to the 0 state seems to be quite high in the processor today. But try it out yourself, and hopefully the processor will be having a better day. So try it out yourself, braid your own Majoranas, find the correlations, find that this is bigger than that and that is bigger than that, and have fun. So this has been my experiment. I did one live for you. This live one was a failure, but there you go. These things happen in science. If we can explain why we got the results, that is when we have a success. If we had a very strong noiseless result, which told us we were getting something different than what we expected, that would mean our theory was wrong, and the entire edifice on which all of quantum mechanics is built would be broken down, and we'd have to come up with a new theory, and that would be even more exciting. But if the processor was having a better day and it was less noisy data, we could see that the data was less noisy. We would see, indeed, as we do in the paper that I've published, that well, I say I've published, I've put it on my blog. You can find the link below. You'll see that we do see these correlations. We do see what we expect to get. It's a bit noisy, but these Majoranas have got braided. We created particles that are impossible, and that's pretty awesome. But what's even more awesome is that you can do it too, and you can do all other kinds of things. So get on the IBM Quantum Experience. It is unimaginably awesome. It allowed me, a theorist, a theoretical physicist, to do an experiment. And if it can allow a theoretical physicist to do an experiment, then even more so it can allow you to do an experiment, because, well, we theorists are pretty unexperimental people. The most hands-on we get is when we touch the chalk, as you saw earlier. The chalk which creates all the chalk dust, which chokes up our computers. But anyway, that's a whinge for another day. Thank you very much for watching. Goodbye.